Hi, everybody. Now we're doing example problems from Chapter 5. Chapter 5. Chapter 5, 5.1. 5.1 says a gymnast with mass 50 kilograms, 50 kg, suspends herself from the lower end of a hanging rope of negligible mass. The upper end of the rope is attached to the gymnasium ceiling. What is the gymnast's weight? And what force and magnitude does the rope exert on her? What is the tension in the top of the rope? Okay, the weight is going to equal to mg. So that's going to equal to 50 kilograms times, g is 9.8 meters per second squared. And her weight is going to be equal to 490 newtons, or 90 newtons. Okay, so she exerts a force on the rope of 490 newtons, and by Newton's third law, it exerts an equal and opposite force on her. Newton's third law states that forces come in pairs. So we're looking at 490 newtons all the way around here. In example 5.2, we're adding some mass to the rope. So find the tension at each end of the rope in 5.1 if the weight of the rope is 120 newtons. So here we go. We've got 120 newtons for the rope. We want to know the tension in the want to know the tension of the rope on the ceiling, and we've got the weight on the gymnast. Okay. So let's see. Let me do it how the book does it. They've got the weight of the gymnast, tension of rope on the gymnast, then we have the ceiling. Yeah, your book does it so nicely. Tension of rope on the ceiling, and then we've got the weight of the gymnast plus the weight of the rope. So these are action-reaction pairs. These are both in equilibrium. The first one is still 490 newtons for the weight of the gymnast on the rope, and for the tension of the rope on the gymnast, it's still 490 newtons. Now we have this guy is 490 newtons plus the weight of the rope, which is 120 newtons. So we've got 610 newtons for the tension for the weight of the gymnast and the weight of the rope. And so that is exerting a force of 610 newtons on the ceiling. The ceiling is exerting an equal and opposite force of 610 newtons back on the rope. All right, that was 5.2. Problem 5.3. In figure 5.3, a car engine with a weight W hangs from a chain that is linked at ring 0 to two other chains, one fastened to the ceiling and the other to the wall. Find expressions for the tension in each of the three chains in terms of W. The weight of the ring and the chains are negligible compared to the weight of the engine. Okay, so we have a situation like this. Here's the wall. We've got a chain here, a ring here. We've got this chain coming at some angle here where this is 60 degrees. And then we have the engine suspended from it. We just call that W. All right. And this guy is T1. And this guy is T2. And this is T3. All right, so this guy, I'll take the sum of the forces at that point right there. So we're going to have, remember this is suspended in an equilibrium. We'll call this the engine. Sum of the forces at the engine. And it's only in the y direction. So that's going to be equal to T1, that's going in the positive direction, minus the weight equals 0. And how about at the ring now? So this is an engine. Sum of the forces at the ring in the X. Okay, so T2 is in the negative direction. So we've got equals T3, and that would be cos 60 minus T2 equals 0. And some of the forces in the ring in the Y, we've got, oh, I'm sorry, this guy, yeah, this is right. We've got T3 sine 60, that's pulling up, so that's positive, minus T1 equals 0. See, note that T1 is negative here because it's pulling down on the ring, but here it's positive because it's pulling up on the engine. All right, now all I have to do is do a little algebra and solve for my tensions in terms of the weight. So I have T1 equals W. 1 equals W. I'm going to go back here, and I'm going to write T3 sine 60 equals W. So T3 is going to equal to W divided by sine 60. And your book gives me that value of, let's see, 1.2 W, 1.2 W. I've got now T3, so now I can go back to this expression and solve for T2. So I'll have a W sine 60 over cos 60 equals T2. And so that's going to be equal to W tan 60. Oh, I don't know what that, oh, let's see, I'll just use your book's value. That's going to be 0.58 W. So T2 equals 0.58 W. All right. And so once again, we solve for this guy here, T1 first, and then we solve for all the forces on the ring. In example 5.4, we have a car being held up by some kind of cable on an inclined plane. Only held by the cable. The brakes aren't on, the engine is off. So, but let's go ahead and read the problem. So here we go. A car of weight W, so this is weight W, rests on a slanted ramp attached to a trailer. Only a cable running from the trailer to the car prevents the car from rolling off the ramp. The car's brakes are off and its transmission is in neutral. Find the tension in the cable, the force that the ramp exerts on the car's tires. Okay, so the tension. So now what's convenient to do in these incline problems is to go ahead and make your X and Y, just kind of shift your axes a little. All right, so do we have the angle? They call this alpha. All right, so what you want to do is let's draw a free body diagram for this guy. So we know there's an mg here, and I got a normal here. I got the tension here. All right, so what I want to do is I want to find, remember, I've got to get this angle right there. So mg is what I know, and I want to get everything in terms of mg. So this guy is going to be the force pulling it down, gravity, this component of mg, and this component of mg is going to be my normal. So I need this angle here. And that angle is the same angle as the angle of incline. But let me go ahead and prove that to you by doing this. Here's your angle of incline alpha. And here's your normal, right? Your normal is normal to the angle of incline. Here's your force mg going straight down. So this is alpha, and we know this is 90 right here. So this has got to be 90 minus alpha. And again, this is 90, so this guy's got to be alpha. So this angle is always the angle of incline. And the acceleration down a ramp is always g sine theta, which is the angle of incline, or in our case, alpha. All right, so I hope that's clear. Let me clear all these. Okay, this is still 5, 5, 4, 5, 4. So we have the tension is going to be equal, it's equal to minus mg sine alpha, alpha is going to equal 0. And the normal force minus mg cos alpha is going to equal 0. So the tension simply equals mg sine alpha. And I think your book calls it weight sine alpha. And the normal force is going to equal to mg cos alpha, or weight cos alpha. That was 5, 4. In 5, 5, you've got a weight 2 pulling this weight 1 up an incline over a frictionless pulley. But let me go ahead and read the problem. Your firm needs to haul. I love the way that they make it all pretty. Your firm needs to haul granite blocks up a 15-degree slope. So now we know this is 15. Out of a quarry, and to lower dirt into the quarry to fill the holes. You designed a system in which a granite block on a cart with steel wheels is pulled uphill on steel rails by a dirt-filled bucket, W2. So this is your, what is this? Granite blocks, and that's dirt. Okay, so include both there. Okay, how much weight W1 and how must the weights W1 and W2 be related in order for the system to move with constant speed? Ignore friction in the pulley and the wheels, and ignore the weight of the cable. Okay. So now I have to have equal tensions here. So let me go in and ahead and solve for that. So for some of the forces in weight 2 is going to be equal to the tension that's going up minus W2 equals 0. And some of the forces in 1 is going to be equal to the tension minus W1, remember that sine 15 equals 0. So now that's good. Let me just write it in terms of each other. So T equals W2 and T equals W1 sine 15. So I'm going to put this value here and get my ratio. So let's see, W2 equals W1 sine 15. So that's whatever sine 15 is. Your book says it's 0.26 W1. So W2 equals 0.26 W1. So that's how they must be related to each other. Problem 5-6, a straight line motion with a constant force. Says an ice boat is at rest on a frictionless horizontal surface. Due to blowing wind, 4 seconds after the ice boat is released, it is moving to the right at 6 meters per second. What constant horizontal force does the wind exert on the ice boat? The combined mass of the ice boat and the rider is 200 kilograms. So we know we've got a mass equals 200 kg. And we have, let's see what else. V final equals 6 meters per second. And let's see, what else do we know? Okay, I guess, oh, we got time, right? Time that we reach delta T equals 4 seconds. So F equals MA. I need to know A, I know M, so now all I have to do is find A. So V final equals V initial plus acceleration times time. This guy was 0, was a dead stop, so we've got a 6.0 meters per second equals A times 4 seconds. So A is going to be equal to 6 equals 6.0 meters per second divided by 4 seconds. That's going to be equal to 1.5 meters per second squared. All right, now I have my acceleration, I've got my mass, so now force equals 200 kg times 1.5 meters per second squared. And that's going to give me 300 newtons. 300 newtons. 5.7. Suppose a constant horizontal friction force with magnitude of 100 newtons opposes the motion of the ice boat in example 5.6. In this case, what constant force must the wind exert on the ice boat to cause the same constant acceleration? 1.5 meters per second squared. Okay, so now we have a force of the wind. We have a force of friction. And so I have a equals to my MA, right? Equals MA. So force of the wind minus 100 newtons equals, what was MA, 300? 300 newtons. I'm going to get 400 newtons. Force of the wind equals 300 newtons plus 100 newtons equals 400 newtons. And that makes sense. The wind has to blow with more force to overcome that friction. So it's going to be the MA plus the frictional force. Problem 5.8 is tension in an elevator cable. An elevator and its load have a combined mass of 800 kilograms. So we know that's 800 kgs. All right. The elevator is initially moving downward at 10 meters per second. 10 meters per second. And it slows to a stop with a constant acceleration in a distance of 25 meters. So delta X equals 25 meters. Okay. What is the tension in the supporting cable while the elevator is being brought to rest? So we've got tension here. We've got mg here. And we also have the acceleration going this way, right? Because it's going down, but the acceleration is slowing it up, so it's going that way. So I need to know my acceleration. I'm going to call this MA, and this is T. Okay. So let's see. I need to find A. So anyway, the force, some of the forces in the Y direction, and we have no forces in the X direction. We're going to have a T minus mg is going to equal to MA. Right? Because MA and T are going in the same direction. But we need to know A. So we've got, let's see, we're going this way. So we have a V final is 0. V initial is going to be V initial equals negative 25. No, I'm sorry, negative 10 meters per second. And delta X equals, that's going 25 meters, but it's going the negative direction, so negative 25 meters. So we have, I'll use our no time equation, which is V final squared equals V initial squared plus 2A delta X. So V final squared is 0. 0 equals a negative 10 meters per second squared plus 2 times A times a negative 25. All right, so subtracting this guy from both sides, I get a negative times a negative 10 meter per second, that's quantity squared, equals 2 times A times a negative 25. And that's meters, by the way. I need to be complete. meters there. So over here we get a negative 100 meters per second divided by, I'm going to go ahead and multiply that and that, negative 50 meters equals A, and that equals 2 meters per second squared. Okay, so now let me just pause and erase this. Okay, now we just solve for T. So from this expression, T equals MA plus MG. So T is going to equal, it'll be easier to just do A plus G times M. T equals 800 kg plus 2 meters per second squared, times 2 meters per second squared, plus 9.8 meters per second squared. And that's going to give me, let's see, I'm going to use the books, 9440 newtons. That's the tension in the cable. 5.9 says a 50-kilogram woman standing on a bathroom scale while riding in the elevator in example 5.8. What is the reading on the scale? So she's pushing down with some force on the scale, and then the scale is reading that force. So whatever the normal force is on the scale is going to be her reading. So once again, we have the normal force here, and we have the weight, and then we have the acceleration there. Okay, so we have the sum of the forces in the y. So we're looking for the normal force equals the normal force minus the weight equals ma. So the normal force is going to equal to ma plus mg. And we already know A equals 2 meters per second squared. So the normal force is going to equal to m times A plus g. And the mass we're talking about is not the elevator's mass, it's the woman's mass inside. And her mass is 50.0 kilograms. So we've got the normal force is going to equal to 50.0 kg times 2 meters per second squared plus 9.8 meters per second squared. And that whole thing is going to be equal to 590 newtons. All right, 590. 510, I asked for the acceleration down the hill. We did a problem very similar to this where we had the car on an incline. It's another problem where you are asked for to solve some kind of body on an incline. So it looks like this, and they call this angle alpha. And you've got some mass here. It's on an icy hill, so which implies there's no friction. So the problem reads, a toboggan loaded with students, total weight W, this is W, slides down a snow-covered hill that slopes at a constant angle alpha. The toboggan is well waxed, so there's virtually no friction. What is its acceleration? Well, from that other problem, we know that the acceleration on an incline is always G sine theta, where theta is the angle of incline. So we have the weight equals mg sine theta. So the acceleration is weight over m. So it's going to be equal to g sine theta. G sine theta on that incline, you guys, always g sine theta. 511 is called two bodies with the same acceleration. And it says you push a 1.00 kilogram food tray, 1.00 kilogram food tray. So this tray equals that. With a constant 9 Newton force. So F equals 9 newtons. The tray pushes a 0.50 kilogram milk carton. So carton equals 0.50 kilograms. Find the acceleration of the tray in the carton and the horizontal force that the tray exerts on the carton. Okay, F equals ma. Okay, so we're finding acceleration. So 9 newtons equals, now the 9 Newton force is pushing both the tray and the carton. The carton is on the tray. It's essentially one mass because it's not going anywhere. It's in an inertial state. It's just like a rider on the toboggan in the last problem. So this is going to be equal to 1 kilogram plus 1.00 kilograms, sorry, 0.50 kilograms times A. So A equals 9 newtons over 1.50 kg. And A equals to, let's see, what do they have? 0.61. 0.61. Oh, no, wait, no, that's, I'm sorry. I got to get my calculator out. No, let me erase that. 9 divided by 1.5, 6 meters per second squared. I was looking at the wrong value, guys. 6 meters per second squared. All right. That is the acceleration. Oh, they did it in terms of G. So they did 0.61 G. They just divided 6 meters per second squared by 9.8 meters per second squared over 1 G. And they did it in terms of G. They got 0.61 G. Did they ask to? They didn't ask to do it in terms of G, but that's an interesting twist. All right, now I need to know the force on the milk carton. So I know that my acceleration now is 6 meters per second squared. Let me stop and clear all this. Okay, so the force on the milk carton, F equals ma. F equals the mass of the milk carton, which is 0.50 kilograms, times 6 meters per second squared. And that's going to be what? 3 newtons. That's the force on the carton. These are example problems from chapter 5 and continued. We're going to start with 512. 512 reads, an air glider with mass M1 moving on a level frictionless air track in the physics lab. The glider is connected to a lab weight with mass M2 by a light, flexible, non-stretching string that passes over a frictionless pulley. Find the acceleration of each body and the tension in the string. All right, so we have a lab like this, so it's similar to this. This is your pulley. Here's your cart being pulled by this mass. And let's see, they call this M1 and they call this M2. And we're supposed to solve for the tension in the string and the acceleration. All right. All right, I'm going to make expressions for tension. And it's important to realize that even though this is in the X direction and this is in the Y direction, the tension is going to be the same because it's the same string and it does not stretch. So let's do the sum of the forces in the X, and this is for the glider. And we're going to get T equals M 1A1. And now the sum of the forces in the Y for the weight we're going to have M2G minus T equals M2A. So those are our expressions for tension. Now for the acceleration, how we did it in the lab and how you can do it here is we know that M2G is providing that force for the acceleration of M1 plus M2 times A. So A is going to simply equal M2G divided by M1 plus M2. All right, now if I want to solve for tension, I'm going to go back here and I'm going to say T equals M1 times this expression, M2, this expression for acceleration, M2G, divided by M1 plus M2. So this is going to equal to, T is going to equal to M1, M2 times G over M1 plus M2. So we have our expression for acceleration here and our expression for tension here. Slide 13 is a problem entitled Friction in Horizontal Motion. And it reads, you want to move a 500 Newton crate. So crate has a weight of 500 newtons across a level floor. To start the crate moving, you have to push with a force of 230 newtons. So F equals 230 newtons. Once the crate starts to move, you can keep moving it at a constant velocity with only 200 newtons. So F1, let's say F static, we'll call that static, and F kinetic equals 200 newtons. What are the coefficients of static and kinetic friction? All right, so we know that our force of friction is going to equal, in this case, mu S times the normal force. And in this case, it's going to be equal to mu K times the normal force, where mu S and mu K are our coefficients of static friction and kinetic friction. So this is static, that's kinetic. Okay, so here's our scenario here. This is you or me pulling this crate with some kind of tension, and we've got a static friction, and we know we're going to move it with constant velocity, so we're not going to have a net force on this. So just before this crate starts to move, we're going to have the sum of the forces in the X are going to equal to the tension plus, and these guys are opposing, negative friction static. And then that would be the max, right? And that's going to equal 0. And the sum of the forces in the Y are going to be equal to your N minus mg equals 0. Okay, so now we know our force of friction is going to equal the tension. So Fs max equals T equals 230 newtons. And we've defined that as T, so Fs max equals mu S over N. So T over N is going to equal to mu S. And now N is going to be equal to mg, which does 500 newtons. So let me go here. We've got 230 newtons over 500 newtons equals mu s equals 0.46, 0.46. And note that is a unitless quantity. Put you on pause, clear my drawing space. And we're going to go through the same procedure for after the kinetic friction. So from the other one, we know that mu k is going to be equal to fk divided by t. So we've got 200 newtons. I'm sorry, fk divided by n, my bad, fk divided by n, because fk does equal to t. We got 200 newtons divided by the n, which was 500 newtons. And we're going to get mu k equal to 0.40. Once again, a unitless quantity. Example 514, static friction can be less than the maximum. So static friction can be less than the maximum. And we are asked in example 513, which is the example we just solved. What is the friction force if the crate is at rest on the surface and a horizontal force of 50 newtons is applied to it? So F equals 50 newtons. Okay, this 50 newtons is less than the 230 newton required force to get it to move. So we know it's going to be at rest. So we have the sum of the forces in the X equals the tension in the cable minus the force of static friction, friction static, and that's going to be equal to 0. And so this is 50. So we can just say the tension in the cable is 50. So we can say the force of static friction equals 50, and once newtons. And once again, from that same equation, we have F equals mu s times n. So we know n, we are solving for mu s. This is F equals 50 newtons equals mu s n. Mu s equals 50 newtons divided by n, and we got that from the last problem of 500 newtons. So now we're going to get 0.1. Mu s is 0.1. Am I even solving for that? Okay, but anyway, that's mu s. All right, in this example 15.5 is called minimizing kinetic friction. It says, in example 15.3, suppose you move the crate by pulling upward on the rope at an angle of 30 degrees above the horizontal. How hard must you pull to keep it moving with constant velocity? Assume UK equals 0.40. So, let's see. Whiteboard. Okay. Ugh. Technical difficulties. Let me pause and take care of this. Okay, so now we have this scenario. I guess this angle is 30. This angle with respect to the horizontal, 30 degrees. And boy, I love the thing in here. Looks so downtrodden. Looks something like this. And there's this. There's this. And that. Here's the poor little guy's head. And we have the string coming from there to there. All right. So, and this is the crate. So this is what we've got. We've got the force is here. Do we get the magnitude of it? Let's see. Pull it up on the rope with 30 degrees. How hard must you pull to keep it moving with constant? Assume mu k equals 40. Mu k equals 0.40. All right, so let's do the sum of the forces in the x and the sum of the forces in the y. The sum of the forces in the x are going to equal to the tension in that string, T times the cosine of 30, cos 30, minus the friction, kinetic friction, minus Fk, and that's going to equal 0. You're moving at constant velocity. The sum of the forces in the y, we're going to get equals T sine 30 plus the normal, right? It's got a normal force, minus the weight equals 0. So the normal minus the weight equals T sine 30, right? That upward pull is going to relieve some of the weight, right, on the normal. Now, in order to keep it moving at a constant velocity, my frictional force has got to equal to that got to equal to that T cos 30, right? It's the frictional force has got to equal to that constant force I'm supplying on that. And by definition, that's going to equal to the normal force times mu k. And I can rewrite the normal force as equaling to the weight minus T sine 30. I forgot this negative here. So the normal force is going to equal to the weight minus T sine 30. So T cos 30 equals weight minus T sine 30 times mu k. And let's see, I am solving for tension here. All right. So coming back over here, let me rearrange my terms.